Now another important example is singular homology of mapping spaces, which I'm going to call dgTop, which is a category where the objects are topological spaces. And for the morphisms, we have to do something a bit unorthodox. Ultimately, we want these to be homology groups, but the problem is that, well, in homology, the differential decreases the degree, but we need our differential to increase the degree. So one very dirty trick you can play is to just take the negative. So for once, we are going to have a complex that is concentrated in non-positive degrees. So for a positive number n, we define the morphisms of degree minus n to be well, the k-linearization of what I'm going to call the n simplices from x to y, which is defined as the k-linearization of the continuous maps from x times the n simplex to y. And then we need to define a differential operator on there. So by linearity, we can just define what d sigma is supposed to be. So if sigma is like a map of this type, we need to make this map take a parameter in n minus 1. So what is this going to be? Sum from I to n, from 0 to n, minus 1 to the I. And then we're going to have sort of sigma composed with the identity on x times the ith face map. What this is just the map that maps an element x in x and an element s in the n-1 simplex to sigma of x and di of s. So this looks sort of a lot like how we defined singular homology, except that we keep around this other argument of sigma. And one can show that d squared is 0, so this indeed works nicely. But now the big question is, what do we mean by composition? So if f is of degree minus n between y and z, and g is of degree minus m between x and y, or I guess we are going to define it bilinearly, so f is really a map from x cross delta n to y, from y cross delta n to z, and g is a map from x cross delta m to y. So now the question is, what is this supposed to be? And well, the idea is to have this thing map element x, and now we have an element s of the n plus m simplex, so we have a map x cross delta m plus n to z, and the idea is to map x times some s to, what can we do? We can apply g to, well, x, we have no other choice, and something applied to s, and then we get an element in y, and we can then plug this element into f, and then also apply something potentially else to s. I'm not going to specify what these operations are, but there is a way to define them, and there is indeed a lot of different ways how to define them, so we have to sum over all of them. So note that this looks a bit like the cup product in singular cohomology, but instead of getting the multiplicative structure by multiplying in our coefficient field, we are instead ultimately composing maps. So unlike the case of singular cohomology, this one here is very highly non-commutative, and it turns out that the other is sort of almost graded commutative. In any case, one can again show that dgTop is a dg category.